think it's, first of all, thanks a lot for coming, everyone. It's impressive to see so many people here early on a Saturday. And I was also impressed when I looked at the attendees, too. A lot of Diffbot customers and partners here, which, I mean, it's neat, but it's also a little bit telling about our field, too. It's like a kind of a small place. And we really need to collaborate and work together if we want to grow the text and analytics community larger, so that we can, we can see some unicorns, some bigger companies. How many of you know what Diffbot is? Have heard of Diffbot before? Raise a hand. Oh, cool. How do you guys know of it? What's that? Okay, so you looked at boilerplate or readability and stuff, and you checked out for the article API? Okay. Anyone over there heard of it? Or I saw a few hands. Okay. So I'm going to be talking today not so much about particular techniques for text analytics, because we do a lot of that at our startup, but I was thinking like what I could really share that would be unique. And I think at our company, we use a whole grab bag of different techniques, but what's really special about our company is, I think, the sort of philosophy and the way we think about these problems, which allow us to do really well. Because Diffbot is really about, I would say, 20 to 40 different classification problems, maybe 5 clustering problems. And the algorithms that are in production perform close to human level performance. And it's a pure machine learning API. So the only reason companies like Microsoft and eBay and these folks use it is because it's something that they can't build in-house. So we really pride ourselves with the quality of the extraction and robustness and speed and so forth. I want to start out talking about just computer vision real quick. So this is a screen cap from the movie Terminator 2, which hopefully you guys have seen. This is when Arnold wakes up and he's naked, and he gets up and he steals his Harley. And so you can see here, it's like, you can see this bike outlined, and there's obviously some sort of occlusion detection going on here with the dotted line. You can see visual Harley-Davidson model 958 analysis. I guess that's the vehicle size, top speed, horsepower, 287 horsepower. I don't know, 600 is code, range. There's an estimate of this Harley to go maybe 798 miles from here. So this is the problem we refer to as object detection, right, in computer vision. It's given a scene, how do you identify the objects in the scene and give them labels, right? In this case, the label, what we call the Y, is Harley-Davidson model 956. So, recently there's been a lot of improvements in the state of the art in computer vision. Show you this slide here, which sort of illustrates, I think this is the best sort of capsule of the computer vision object detection improvements. So this is ImageNet, and this is the classification error in 2010. It was 0.3, right? So 30% of ImageNet was classified wrong. And then 2014, it's less than 10%. And this is actually out of date. So GoogleNet published at, this is I think 6.6 crossval, or test error, I think. Shortly after that, Baidu computer vision team, led by Andrew, published a 5.98. And then a few months earlier, just like in February, some folks at MSR published a 4.94. So to give you an idea of what this means, a human level performance on this task. So this is a task of about 1,000 classes and 1.2 million training images. Human level performance of human labelers is 5%. So the latest MSR number is beyond human level performance on image classification. And I don't think this graph really does justice to how big of an improvement this is, because when you're here, you're basically, it's kind of like, it's pretty much random, and sometimes it's right? You can't really trust it when it's at 0.3 classification error. And now it's performing better than an expert that's looking at these images all the time. So in terms of how it feels, it's like really like a step function up. It's not just like a linear improvement. It's like it feels like it's moved from the realm of something that's not useful. It's pretty much random and slightly better than random to something that's better than human and can be used in certain limited applications, right? So this is one of the great successes of AI recently. And the reason I bring up computer vision to start out with in this event that's about text analytics is I want to ask, how are the computer vision guys able to achieve this? So see, there's more people coming in. Can you try to move to the front of the room? So, yeah. So I was in the Stanford AI lab. So I remember back around this time when this ImageNet data set came out, the sort of general attitude was, you're building a label set of images that's not, that's not fundable research. Like research is working on algorithms, right? And improving your method, and writing a paper talking about a technique that outperforms, an older technique. And here these guys were building this data set, right? That's something you would have an undergrad be doing, right? As an RA maybe, right? But this effort of collecting 1.2 million labeled images is what ultimately propelled us from not useful to better than human level accuracy, right? And so that's interesting. But so we've basically sort of solved part of the vision problem of object classification in a limited domain, right? But how do we apply this to these other parts of the brain, right? Like the motor cortex, I think we've got it pretty nailed. We've got robotics, we've got control systems. You can see it's getting better and better. Our ability to manipulate objects in the world is pretty much as good as human or better than human already. You've got robotic arms that can lift more than a human, right? You've got audio processing, it's getting improved. We have algorithms like DSP and stuff that can process audio signal, right? Some of the same kinds of techniques as in speech to decode it. But what about this frontal lobe? What about getting this fundamental AI problem, right? So a lot of us got into this field, right? Which is a pretty niche field because we want to build systems that are intelligent, and that hasn't happened. And I want to ask, how can we do with natural language understanding and these other AI hard problems the same kind of improvements that have been done in computer vision and back in ImageNet, right? So one of the ideas we have at Diffbot is sort of one of our philosophies is, what if actually we don't need to, what if one of the algorithms that we have today already is an algorithm? Because if you look at ImageNet, there weren't really any new algorithms created here. A new big data set was created, and it turned out that convolutional neural networks, which is a pretty old technique, was the perfect sort of algorithm that we had already invented that worked well with this big data set to produce these kind of gains. What if we already have the NLP algorithms that we need, we just are lacking that same kind of really big data set, right? That got me to thinking about how we would go about building this sort of really large data set. How large, you might say? You might think, how big would you need it to be? So this was 1.2 million. before this, you had image label sets that were like in the thousands, right? Or at best tens of thousands, painfully manually labeled and curated. What would you need for language? What would you need to teach a system about the concepts of our worlds? Well, how many different classes are there? For ImageNet, there's only 1,000 classes, and they've got 1.2 million labels. But my rough approximation of how many concepts there are, Wikipedia has nowadays around 5 million entities. It's sort of like this, so it's actually slowing down. So I think it's going to approach maybe around 10 million entities in Wikipedia eventually. So like if you had 10 million classes of things, how much data would you need? And assuming sort of like the amount of data has to grow super linear to the, I would say quadratic to the number of classes, I think a good goal is to shoot for like 1 trillion labels. So this is sort of like sort of a leap of faith or a belief is like, how could NLP be changed if we had a label set that had 1 trillion labels in it, right? Tag data. Maybe the techniques that we already have, with parsing and grammars and using probabilities, would lead to an intelligent system. And so this is something that I started thinking about maybe a few years back. And I started thinking about how could we build like a machine that could output 1 trillion labels? Like what sort of conditions and environment would have to be there? And if we could get 1 trillion labels, just maybe we'd have a shot at building truly intelligent systems. So just think about that for a second, like as an exercise. Like how would you get 1 trillion labels? Well, there's some things that obviously wouldn't work if you think about that kind of scale, right? So human labeling isn't going to get you 1 trillion labels, right? So creating and annotating data sets. If you look at ImageNet, part of the reason they were able to build this data set, obviously they had a team that was motivated and cared about it, but it was also because there was technology that they leveraged here. So they used Google Image Search and Google Translate, right, to query these synsets and get a whole bunch of matching images. And then they used things like Mechanical Turk, right, to go through and make sure that those images were of that concept, right? And so those things didn't exist before. So even if this is the reason, sort of like people had built label sets for images in the past, but they didn't have Google Image Search and Mechanical Turk, right? So there's some enabling technology that needs to be in place. So human labeling itself will never scale to this number of labels. And it's also, I think, pretty obvious to me that any kind of semantic markup or microdata or other formats, they'll never get you to that scale either. And those have a host of other problems. It's not comprehensive enough. You'll never be able to have the perfect schema. People don't mark up their pages with the schema. They lie sometimes when they're marking up the pages. There's all sorts of weird interests. So if you think about 1 trillion labels, obviously the data source that goes in and a 1 trillion label comes out, that data source has got to have more information than the output, right? And if you think about what sorts of corpuses are of that scale where you could have more information going in than coming out, I think it becomes really obvious that the web is the best resource we have of human-generated information in documents out there. But now you've got a bunch of web pages, right? So this goes back to building this machinery again, this factory basically. What can you do with web pages? How do you go from web pages to labels, right? And so there's a journey that our company is taking to try to get closer and closer to that. But we're basically building the fundamental layers that can take web pages and transform them into cleaner and cleaner versions automatically, and output these tuples. So what Diffbot does is, this is sort of our key insight, is web page extraction is a computer vision problem. So this sounds like non-intuitive to other people that do scraping or web page extraction. They see this as regexes and writing patterns against the markup of the page. But the way we see it is, here's the print version of the New York Times. Here's the web version of the New York Times. These are essentially scenes from the digital world that aren't random. They're generated by some underlying model, and we as human beings can parse them, make sense of them instantly. Like, even though you can't read the text of this, this probably just looks like a blurred line, from 10 feet, 5 feet or 10 feet back, you can still make out what this is instantly. You can tell that, this is probably a headline. Here's the text that goes with it. You can't see what I'm pointing at, but you probably know this is the author, right? There's just so many conventions in here that date back to thousands of years, that to sort of have, there's a generative model in how these web pages are organized that humans can instantly parse, right? So how can we teach or teach an algorithm to essentially simulate the same parts of the brain that we all employ when we're looking at web pages for, hours on end, in a given day, right? So you can think about how much brain power in aggregate human beings are using just reading and understanding web pages right now, and how much you could save if you had an algorithm that could do that automatically. So we use computer vision, and we're building the base layer of this machinery right now. From human documents that are intended for humans to read, how do you get a more structured version? And then from there, we can get even more structured and even more structured. And I'll explain the steps we're taking, along that more structured path. Just as an FYI, we now have a index of this sort of what we call layer 1, lightly structured objects that is in the we have about close to 500 million, and in terms of the tuples, we have around 3 to 4 billion right now. So the Diffbot technology as a backend service powers parts of the Bing search engine, like DuckDuckGo, Instapaper. Whenever you are like Instapapering a news article, it's basically passing that URL into Diffbot servers. We're converting it into a structured article, and then that's what shows up in your Instapaper account. And various different other companies, like Radian6, use us to monitor what people are saying on these web pages. And we just released a discussion API that can automatically ferret out the discussions. So so we think that the right approach, and Diffbot uses, we've tried every single approach, we use whatever works, is using the visual features. Another reason is, here's like the markup for like this page, right? There are so many different ways that the HTML can look that generate the same look to the human, right? So why not just work at the layer that the human sees, right? Rather than trying to infer, right, based on a whole bunch of hard-coded rules and things of the HTML syntax, which is unreliable, and which go away basically when we move to a new kind of document presentation technology. Like if you go to Flash, or if you go to like HTML5, then those conventions and programming things all go away, right? So it's another reason why I think visual is so important. Let me explain the overall architecture of how Diffbot works. So we basically start out, the easiest way of using Diffbot is you pass us a random URL. And the first thing that we do is we have developed our own custom renderer that takes in that URL and simulates what the human sitting in front of their computer in a browser is doing. Their browser's rendering the page, it's executing the AJAX, it's downloading the CSS. We've hacked WebKit so that it's about 10 times faster than Chrome. We've thrown away like things like memory management, bookmarks, all those things that are human affordances that bots don't need when they're analyzing web pages. And then the basic point of the rendering is to produce features for the machine learning algorithm. So our machine learning methods take into account everything that the human sees about the page. So we have pixel level information, X, Y, height, width, color, alpha, positioning information, layout information, as well as everything that the browser has access to. Excuse me. So because we control the rendering process, we know the byte sizes of all the headers. We can see the time of flight, how long this HTTP request took. We can see the video stream that's being played in that video that's on the page and analyze the frames of that video. We can see AJAX calls, things that are in the headers. So, and we can also see the markup too. So we can also see what's here. So why disadvantage your bot, right? If you're trying to build a bot that's super accurate, and people would pay money to use, right? You want access to everything the human sees up here. You also want access to everything that the program sees down here. And there's information that we can mine from here too. So this is also a language that's, by the way, it's intended for humans. So who is it that said that? That said source code is mainly for humans to read, right? And secondarily for computers to compile. So we built language models for the variables in the programming language. We built language models for URLs, right? So you can think of the analog of WordBec, but for URLs, which have a different generative model than the natural language, right? But it's also a human language in the way we format URLs and CSS classes and things like that. This is what I mean when I say Diffbot has, literally like 20 to 40 classification problems. It's our company is basically a machine learning algorithm with a light API wrapper around it. So then we got all these features, and then we've got labeled data. We've also got a whole ton of unlabeled data from crawling the web and from URLs that customers and partners provide us. And we use semi-supervised techniques, and we use a lot of them. So it would take me too long to describe all the different machine learning techniques and hacks, and we use whatever we can get our hands on, and that works. And we have methods of evaluating the performance, the precision, and the recall on a nightly basis, and pushing them to prod. And we have methods of seeing a web page and having that update the model and being pushed to prod, and learning about the site structure as it's crawling the structure. So there's an interface that, the easiest interface to using the Diffbot as a product is you pass it a URL. It performs the classification, determines what kind of page it is, and extracts it as structured data. Another way of using Diffbot is you give it a domain, and it'll crawl the whole site. So you can say, give me all the products on jcrew.com, and you get back just this structured database of all their product catalog that's queryable. So when we're doing that crawling, we can learn about the generative model of the pages by seeing a lot of the pages on the site, right? So there's a lot in the machinery. And last year, we acquired a minor search engine. So we have this really robust crawling infrastructure that's capable of crawling the web, which very few entities do nowadays in the US, unfortunately. So when I said classification, let me describe how we think about that. So if we go back, our goal is to try to basically convert the web into a structured format so we can get a lot of labeled data that can be used for all the different things that you guys are building in this room, right? All kinds of things that can be done once you have clean text, once you have the entities that are in data in a more structured representation. So in order to achieve that goal, we want basically our bot, when it encounters a page, to be able to automatically determine what kind of page that is and extract it into that page's schema, right? Without any human intervention. So this was about 2.5 years ago. We partnered with Twitter and one of our customers, DuckDuckGo. So this is like from the Twitter Firehose sample. So this is a particular sample of URLs. It's sort of the shareable web. So it's a biased sample of URLs. But this breakdown shows what types we found, right? So 36% of tweets, the links in a tweet are to an image page. So this was information that nobody really knew before. I mean, they knew that some percentage is Instagram, right? Some percentage is TwitPic, but they didn't know that we sort of created this, web page ontology. 16% of the URLs that are shared are to article pages. 9% are to video pages, 8% are product pages, 7% are front pages, 9% are these. And the page types that Diffbot has released in production include image, article, video, product, front page. And as of 2 weeks ago, we also have discussion in FAQ. So we can, of the shareable web, we can process around, I think it's around 75 to 80% of the web. Just, and then when it's one of the ones we don't support right now, we just put it into other. So we'll just save it for later. But we think that if we, after a few more months of development, we can complete these other page types and be able to get like 98% of the kinds of pages that are on the web. And then at that point in time, then we can actually start, we've actually already started actively crawling the web and starting to bulk convert the web into this structured form. Let me give, product API. So let me give like a demo. So let's see if this works. Oh, this is, all right, that was a little fast, but that happened live. So, so if you remember back to the first slide, Arnold Schwarzenegger saw the Harley, and he determined it was good. So here's a product page. This is typical of what our customers do. You can just pass this page, or any page, you can just paste it there. And Diffbot will say, it's of type product. It's a product, and the product's title is this, right? This is the description of the product. Here's the price of the product. It's product ID. Here's, it's found the image of the product. And the image has a caption. It's determined that there's an offer on the page, an SKU. I think there's more too. There's a JSON view. Human language English, that's an easy one. So you can imagine this bot right now is crawling the web and automatically doing this for every product page out there. And now we have a lot of these, on the order of close to 1 billion. So we still got a lot to do. So the next basic steps in our roadmap are, we've now got a whole bunch of these JSON objects. Some of them are from us crawling, some of them are from customers, and some of these higher volume customers that send us URLs. And they're just all just sort of like there in this big goo right now, right? We're working on normalization and entity resolution. So this Harley Davidson, that's sold on this one site, and this other site right now are two separate JSON objects. But they are actually, they're the same product. They're just being sold by two different places. There's two different offers, right? So we're working on methods of fusing those objects together so that we have a coherent entity. So that's an example in the product space. But if you notice, one of the other page types is like profile. So that's people, right? So I have a LinkedIn page. I also have maybe a Facebook page, right? And there's different information on there, but it's really the same person. And those fields should really be merged, right? So how do you do that at large scale across the web reliably? So we're building it up in layers, but the goal is that at some point as the bot's crawling the web and discovering more and more pages, our confidence level about the objects in the real world just increases automatically without any, you can imagine, if you see this Harley enough on enough different pages, you start becoming increasingly confident that, that Harley has a certain mileage, it's certain dimensions, it comes in these colors. You start becoming increasingly confident that this chair, is white, has 4 legs, has a certain height and width, it's a certain price at different places, just from seeing it a lot, right? So as it's crawling the web without any human input, we want to get to a point, which we're not at yet, where it's just increasingly confident about all these entities, and it can unify them in a way that you can now query across it and say, give me all the objects or give me all the things that match these criteria, and then sort of like an SQL kind of query, and just get back all the matching things, see where those are referred to on different pages on the web, right? So you could actually do stuff with it, right? Like you want to buy that Harley, right? Then you eventually need to go down to the guy that's selling it, and we're working on things that can actually execute the purchase flow completely visually, like click the add to cart button, put in your payment credentials, put in your email address and your home address so that the motorcycle arrives at your doorstep, right? So that's the overall vision of the company. So that concludes my presentation. The final thing I want, so thank you all for listening to it. For everyone that's at this conference, just like as just like a token of appreciation, no pun intended, I'd like to give everyone here actually a free paid API token to our standard plan, which it costs $3,600 a year, like that you pay for it. So for personal use, yeah. So no one outside of this, no tweeting or sharing. But if you want to, the way to get it is just when you generate a token on our site, just say that you talk to Mike or something at text, TBTV. Thanks a lot. I'd love to open it up for questions, discussion. Yeah. Yeah. So yes. So we do save it, but then obviously for things like products, the properties of that object actually change over time. So some of our customers want to track the price over time and stuff, so they'll recall it again. So you'll have to know when to be able to use the cache and when not. Is that what you wanted to know? Okay. Yeah.
So you mentioned that you technology that you use is sort of different technologies out there, so Stanford AI results. Do you find that you often have to tweak that methodology to the changes, or is it, how often do you iterate on what you do?
Yes. So we sort of purposefully set up our company in a way where it would be unscalable for us to tweak anything, because people can send us any URL, right, and it's got to work. It's also a paid API, so if it doesn't work, we don't get paid. So there's sort of a forcing function that it has to be really good, has to be very precise, and we're a small team. So we're 14 AI people working out of a house in Palo Alto. We're all technical. We don't have any dedicated sales or PMs or anything like that. We're not the capability to do customer-specific like fixes and things like that. In our product, we offer a way for the customer to train Diffbot. So if they find a page where they actually want to add a field that's not in our schema, like let's say, I don't know, it's something about, I don't know, a car site, and there's some field in there that we don't want to extract. There's a WYSIWYG interface that allows a PM to just point and teach Diffbot, extract this, and then it'll add a field in real time to their API calls. And that also adds a label to our training set that we can then use to refine our model. Yeah.
How long does it take to follow 1 million?
1 million pages?
Yeah.
Well, it depends on if you do it sequentially or in parallel. It depends on the robots.txt policy. It depends on whether sites block you. It depends on whether there's spider traps or other weird crawl loops on the site. It depends on how complicated the site is and it's, what's needed to render the page, right? If the site like is one of those where you have to like scroll down for more stuff to load and there's like this infinite scroll and stuff. So Diffbot handles all those kind of cases. On some news sites, like a pop-up will come up, right? And Diffbot actually can visually identify that pop-up and close it and follow the next button all the way through to like the 10 pages of the article needed to concatenate together that article, right? So totally depends on the site. But it's roughly, you can think about it as like how long would it take the site to appear in your Chrome browser, right? Because we're using the same core rendering engine. It's just we made it, slightly faster. Yeah.
So the way it's getting more and more interactive,
Mm-hmm.
I
Yes.
think the example you had,
Yes.
you need sort of features, the language defaults are able to find directly.
Mm-hmm.
How do you handle that?
So, well, I just gave an example, right, of the way Diffbot can actually interact with the page to end up at the state that it wants to analyze, right? So, what is your question though? It's how do you do interaction, or?
Yeah. How do you extract? How do you know where to retry?
Yeah, we see it really as an AI system. So you've got a renderer here that displays a certain state at a certain point in time, right? That's like one frame of a video that's playing, right? So you may see a pop-up come up and visually identify that. Then you have to send an action back to the renderer to tell it to close that. And then you have to serialize the rendered snapshot of the page again, right, in order to get what you want. Or in the case of the next, you have to like keep clicking next or keep scrolling to get everything. Yeah.
This kind of really a game changer. I'm just wondering what kind of novel applications have you opened up that you can talk about? How is it that people are building on top of this?
Yeah. So I mentioned like, I looked at the attendees and there's like 6 or 7 Diffbot customers like that came to this. So they're wide ranging. They anywhere from just NLP research, right, getting a ton of articles, to news applications, to products, e-commerce, to now with the discussion, user review mining, discussion mining, brand monitoring, content marketing. Does that give you a sort of flavor of the clusters? Yeah. But we see it as, these apps are super critical to us because they provide the training data for the system as they use Diffbot. And then at some point, we'd like to, open up this essentially large structured index and allow people to contribute, even more structure to it, right? People doing processing on layers on top of Diffbot should be able to write that back to the graph so that other people can use it. But that's what I think is going to get us closer to that goal of getting a trillion labels. Yeah.
One of the challenges with that, how do you, for example,
Mm-hmm.
is knowing where to draw the line of maybe formatting entity, is some people might call that stack, or exactly entity versus one piece up here versus one entity. How do you talk about deciding components?
Yeah. That's sort of like one of those like classic NLP questions whenever you have some sort of fixed ontology. I'll tell you what we do right now, which is, I told you we have this like big goo of JSON objects, right? And we don't actually try to resolve them into hard clusters at index time. What we do actually is at query time, we have a really fast clustering algorithm that can query the things that we think go together and present that back with some threshold. But we're still working on that. It's a fair point. Whenever you're clustering things, think of it, you have to choose like what's your cutoff point, like what's K, right? Or if you're doing hierarchical clustering, like where's that line? For different customers, it may be different things. In the news space, right, is all the news that is about the same event form a cluster, or is it, this same news article that's on many different sites a cluster? So we don't know yet. Maybe make it user selectable, like that threshold. Well, I mean, our goal isn't just to hit some vanity number. Our goal is to try to produce an intelligent system, right? So, I don't know, yeah. Yeah, we have, let's see. There's, this is like the best study we know of. It's actually on GitHub. It's like some PhD student did it as his master's thesis, comparing different text extraction algorithms. So this is, keep in mind, this is just text extraction. So this is like the article API, which is only like one of like the 20 APIs we have, right? So, because we don't even know of any other libraries or automated methods of doing product extraction. There's just no one to compare to. But for article, this guy got a decent data set. And here's the F1 scores comparing Diffbot to boilerpipe, which is open source. Uses some machine learning. Readability, which is a bunch of hard-coded things in JavaScript. Alchemy, and Bedley, and Goose. But you can look at that if you want. And you can download the data set too if you want to validate it. Yeah. It's still pretty nascent right now, so we'll extract some things like the video metadata. So we'll try to get some tagging, duration. The discussion functionality means we can get the comments of a video, but we don't do a lot of deep analysis of the video itself right now because it's too expensive. Yeah. Okay. Yeah. Oh, okay. Yeah, so I sort of mentioned before, the machine learning algorithm has access to all the WebKit internals. So that includes the, so we don't actually have to do OCR on the image to get back the text that's already there, right? We could, but it's already there, so why do that? So we can, because we have hooks deep, we've basically instrumented the WebKit render. We know that, this rectangle on the screen corresponds to, this text node in the DOM. I can just get it directly. But many times in the article API, the correct output isn't actually even a DOM node. It could be what we call a disjoint node list, or a whole set of nodes that aren't even continuous on the page. All right, so all you have time for? Yeah, I'll still be here, so I'd love to stick around if you guys have more discussion or questions. You have interesting ideas. But thanks a lot.